Асад. На принтере, где принтер внутри стоит, мои наушники принеси.
Yeah. Thanks.
All right, YouTube wasn't working, so
Где
we'll have
принтер
to
стоит,
go
мои
to
наушники
Zoom
принеси.
today. It's going to be bad.
It's okay. You don't need to get
Наверху, где
Zoom's
я
not
сижу.
as good as YouTube, but we'll make do. Yes, please do mute your mics. All right. All right, anyways. How are we doing?
Good.
Let's wait a minute or two until everybody comes in. Questions while we're waiting? Not sure why I can't hear what. All right. Anyways, apparently, right? It's because I didn't wear a black T-shirt that YouTube failed us. How do you know when to stop using the chain rule? You stop when you've taken the derivative, right? If the question is asking for the derivative of sine of x squared, well, the derivative of sine is cos times the derivative of the inside. The derivative of the inside, you know to be 2x. That's it. So it's when you know what the derivative is. Implicit differentiation is not part of the midterm. It stops at the chain rule. And yeah. Well, you take the derivative of the inside. Inside is x squared. It's not 2x.
And like, what up, bitch? I want to fucking kill myself. And then she's over here. She's all like,
Okay, can I mute everybody? I thought everybody was muted to begin with. Let's see.
Because like, I'm just over here and I like walk in like, two younger sisters, they made the same dumb fucking tattoo mistake. So Melody was 18 in college last year. She got
How do I mute everybody?
Year two dude would give her a sticker punk tattoo.
All right, I think everybody should be muted now. Is that good? Very good. All right, still unmuted? Maybe it's from my end. I think everybody's been muted. You see unmuted signs.
I decided to make her very favorite black bottom pie. It's a family favorite, taking 3 eggs, milk powder, spill it all over like mother, like daughter. Corn syrup, sugar, a little bit of vanilla, and some butter. We're gonna get that a good stir up, and we're going to.
Denisha, no, Denista. Denista needs to mute apparently. How can I? It's good now? All right. Everybody's good? All good? Great. All right, let's get started then. So let's go back to the, YouTube is much better. Let's go back to the definition of the derivative. Recall that the derivative, the limit definition, the limit is as h goes to 0 of f of a plus h minus f of a over h. The certain books have different have a different definition of that. Have a different definition, a different limit definition for the derivative. And let's see how that happens. If we make a change of variables, if we let x be a plus h, then as h goes to 0, as h goes to 0, x goes to a. So we can rewrite this as the limit as x goes to a. This is f of x minus f of a. And the h here is really x minus a. So a lot of books, including ours, includes this as the definition of f prime of a. And in some instances, it might be easier to work with this than with that. I don't really use this one, except in the following situation to introduce the idea of linearization. What are we saying? We're saying that this limit as x goes to a is equal to the derivative. So for values of a close to, for values of x close to a, well, let's do it here. Values of x close to a, this thing is going to be very close to f prime of a. Right? That's what the limit means. It means the behavior of this for values very close to a is that. So, yeah. And if you multiply both sides by x minus a, and you bring the f of a to the other side, in other words, solve for f of x, we have that f of x is approximately f of a plus f prime of a times x minus a. This is known as the linearization of f, or linear approximation or tangent line approximation. Because you might have recognized if you set y equal to this, you actually have the tangent line. You are able to get something similar from this original one, absolutely. Absolutely. But I think this one is the better one because, right, you recognize this as being the tangent line. Yeah. So, I mean, what we're really saying is that for values very close to A, the function can be approximated by its tangent line. That's all that's happening here. Let's take an example. So consider the following scenario. Suppose that we want to approximate 1 over 4.002. We don't have a calculator. We're hoping to get a nice approximation for this, right? And what are we going to do? We're going to define a function, choose a good value of a, for which we know the function and its derivative, and then evaluate. So if we let f of x be the function 1 over x, with a equals 4 in the linear approximation, well, you know what f of 4 is, right? That's easily seen to be 1/4. You know what the derivative is. The derivative of 1 over x is minus 1 over x squared. And the derivative at 4 is minus 1 over 16. So if we apply linear approximation, so linear approximation f of x is approximately f of a plus its derivative times x minus a. If we let a be 4 and x be 4.002, so f of 4.002 is approximately f of 4 plus f prime of 4 times 4.002 minus 4. Right, so this is 1 over 4.002. This is approximately 1/4 plus the derivative So minus 1/16 times 0.002. So that is the linear approximation. Let's try another one. Is this related to power series? Very nice, right? For those of you familiar with power series, this is really the first two terms of the Taylor series. Could you prove it graphically? Well, graphically, what's happening? As I suggested earlier, you have some function, and we're saying that very close to A, the function and its tangent line are almost the same. And that's it. This is the tangent line. This is the function. The function and the tangent line are almost the same. That's all that's happening. Jamie, apparently your mic is unmuted. Shall we try another one? Same question. Approximate cosine of 29 degrees. On the x-axis, this is an A. I'm saying that for values close to A, the function and the tangent line are almost the same. So they are not equal, right? That's why I've got this squiggly equals here. It's an approximation. All right, cosine of 29 degrees. Let's see. Let's see what happens. Welcome, Hannah, where we've just introduced linear approximation, also known as tangent line approximation. So this is the equation we're looking at. Your very close to A, your function is approximately equal to the tangent line. Correct, Michael, but we're not going to go any further into the series. We're just looking at the first two terms. So just the tangent line or linear approximation. Linear, right, because you have a polynomial of degree 1. Cosine of 29 degrees, you know what you're going to do, right? First of all, it's important to switch this to radian measure. So 1 degree is pi over 180. And so 29 degrees, well, let's say 30 degrees, we know to be pi over 6. So this is going to be pi over 6 minus pi over 180, or 29 pi over 180. If we define f of x to be cos x, where x is measured now in radian measure, you know the derivative is negative sine.
Grammarly does more than catch errors. With Grammarly,
So your function at pi over 6, or cosine of pi over 6, you know that to be root 3 over 2. Sine of, well, the derivative at pi over 6, which is minus sine of pi over 6, you know that to be minus 1/2. Rowan? Apparently you're muted. Please mute yourself, everybody can hear you. And linear approximation tells us that f of x is approximately equal to f of pi over 6 plus f prime of pi over 6 times x minus pi over 6 for values of x close to pi over 6. So if we plug in, so I mean in this case, what are we saying? Cos x is going to be approximately root 3 over 2 plus or minus 1/2 times x minus pi over 6. And if we plug in, if we let x be 29 pi over 180, or pi over 6 minus pi over 180, right? Then we get cosine of 29 degrees, or 29 pi over 180, is equal to root 3 over 2 minus 1/2 times negative pi over 180, or root 3 over 2 plus pi over 36. All right. Sean, question? No? Is there still a lag on this? 30-second lag like on YouTube? Sean can't unmute himself. Right, and yeah, that's, I mean, I made it so that people could not unmute themselves. I'm not sure why some people are joining unmuted. It should, everybody should have been muted to begin with. So Jacob is suggesting to say number, and you'll repeat it. Let's say 17. How long does that take? Well, okay, so pretty. Very good, very good. It's instantaneous. All right, got it. So at least that's a bit better than YouTube. Sorry, Sean, you don't understand the step between what cos x and let x be that? Well, we're trying, the original question was to approximate cosine of 29 degrees, or cosine of 29 pi over 180. Right, so that's what we're trying to approximate. That's what we're trying to approximate, and we're going to approximate it using linear approximation, also known as tangent line approximation. So that's what our tangent line approximation says. We chose pi over 6 because it's very close to 29 pi over 180. Right? It's very close to 30 pi. 180, which is pi over 6. Right, so we have to choose, right? What we're saying is that the tangent line is approximately the same as the function for values very close to A. Not if you go too far away, right? If you're very far away, then you see that there's a huge difference between the tangent line and the function. There are not multiple answers. You cannot choose a different degree. It's called linear approximation because it's degree 1. Questions here? How are you doing with this? Exactly that, Jacob, right? The right side represents the tangent line. If you set y equal to this, it's actually the equation of the tangent line. Absolutely. So that's why it's called, I've rubbed it off now, but it's often called tangent line approximation. Could we have gotten the same answer if we had worked with degrees instead of radians? Well, you know, we saw from the chain rule that if cosine is measured in degrees, the derivative of cos is not negative sine, right? So you're going to have to account for that, and it's going to be terrible. So let's not do that. We have decided that radian measure is what we want to do, and let's stick to radian measure. Very well. Let's move on to hyperbolic trig functions. It's going to be posted on my courses for sure. Maybe I'll upload it to YouTube as well. I'll see if I can make that happen. Unless otherwise stated on the midterm, you can assume x is in radian. Absolutely. Hyperbolic trig functions. You don't have to print out the midterm. Just do your work on a piece of paper, take a picture of it, upload it to the space provided. Does it not say simplification? If it doesn't say, then I guess it's not necessary. I don't remember if it says or not. There will be part marks attributed. It depends how bad your answer is. You can work on a tablet and upload screenshots as well. If it doesn't mention, then that's what it is. It doesn't mention, so yeah. I mean, you should justify every step. Absolutely. It's all good. Hyperbolic trig functions. Let us define hyperbolic sine of x as e to the x minus e to the minus x over 2, and hyperbolic cosine of x as e to the x plus e to the minus x over 2. What do I mean by justify? Well, exactly that. Let's just say, show all your work. Show all your work, and that will be sufficient. Hyperbolic trig functions, here we go. Hyperbolic sine of x is defined as e to the x minus e to the minus x over 2, and hyperbolic cosine of x e to the x plus e to the minus x over 2. Well, I mean, a lot of you, I'm sure, have never seen them before. I'm defining them right now. Understand that it's not sine of hx, right? It's hyperbolic sine and hyperbolic cosine. Yeah, seems about right. We did 3.10 and moving on to 3.11. I mean, I'm not sure it's 3.11, but I know for sure that it's a different section. I'm defining the term hyperbolic sine and hyperbolic cosine right now. So, I mean, it's just a combination. I don't know about underbolic. It's just a combination of exponentials, right? E to the x and e to the minus x. So nothing to worry about. You're familiar with exponentials. You're familiar now with hyperbolic sine and cos. The obvious question arises, why would we want to do that? Why would we want to define this special combination of e to the x and e to the minus x as hyperbolic sine, or this as hyperbolic cosine? There are a few reasons. The first of which is that hyperbolic cosine comes up naturally. If you were to put a wire, like a telephone wire, between two poles, under the weight of gravity, the wire will naturally take on a hyperbolic cosine form. So these arise naturally. And in defining these, why define them like trig functions? Well, they have many properties that are similar to trig functions. Right? Not exactly the same necessarily, but similar. Well, it looks like a white parabola, and in fact, you're right, it kind of does. But so does this. So let's get an understanding of these hyperbolic trig functions. And you know, I've written down hyperbolic sine and hyperbolic cosine, but of course, you can expect hyperbolic tangent to be like its trig relative, hyperbolic sine over hyperbolic cosine. So if it's this over that, you see the twos are going to cancel, and that's just e to the x minus e to the minus x over e to the x minus e plus. And similarly, hyperbolic cotangent is going to be the reciprocal of this, hyperbolic cosine over hyperbolic sine, or e to the x plus e to the minus x over e to the x minus e to the minus x, and so on and so on, right? Let's finish that up. Hyperbolic secant as 1 over hyperbolic cosine, or 2 over e to the x plus e to the minus x. And finally, hyperbolic cosecant as 1 over hyperbolic sine, which 2 over e to the x minus x. Right, so we have these 6 hyperbolic trig functions. And, you know, just for fun, let's talk about hyperbolic sine of 0. Well, Nandini, you're giving it away there. We'll see those momentarily. Hyperbolic sine of 0, what happens when you plug in 0? E to the 0 is 1, minus e to the 0, which is 1, over 2. That's 0. So hyperbolic sine of 0 is 0. Just like sine of 0 is 0. What about hyperbolic cosine of 0? That's e to the 0 plus e to the 0 over 2, which is 1. Hyperbolic cosine of 0 is 1, very much like cosine of 0 is 1. All right, that's nice. What about hyperbolic sine of negative x? What happens if you plug in negative x? You get e to the negative x minus e to the negative x over 2, or e to the negative x minus e to the x over 2. And if you factor out a negative, that's e to the x minus e to the minus x over 2. In other words, minus hyperbolic sine of x. Conclusion? Did we give these things a name? What happens when you can pull out the negative? Right? Hyperbolic sine is an odd function. Very much like sine is an odd function. How do these look graphically? Well, let's talk about this one here. You know what e to the x looks like. You know what e to the minus x looks like. So if you add the two together and you divide by 2, if you take the average, right? I mean, it's going to look something like this. So different from cosine, it's not, it doesn't, first of all, it's not periodic. It doesn't look like a wave. It's not bounded. So it kind of looks like a parabola, but not exactly, right? Because you know that exponentials grow much faster than x squared. But yeah, right? So we saw that hyperbolic sine of x is odd. I think it's clear that if you plug in negative x, you get e to the minus x plus e to the minus x over 2, which is really e to the minus x plus e to the x over 2, which you recognize again as hyperbolic cosine. What are we saying here? Hyperbolic cosine is even. Thank you, Michael. What's an important property of sine and cosine? You know that sine of theta squared plus cosine of theta squared is equal to 1. Well, what do I want to do here with hyperbolic trig functions? I want to point out that there's really nothing going on. We define hyperbolic sine this way, hyperbolic sine that way. So it's really just a combination of e to the x and e to the minus x. And you're very familiar with these functions, so there's no issue in playing around with these two things. Exactly, it's just scary because you're learning it for the first time, but there's really nothing there. Right? Let's look at this important trig identity for sine and cos. You have a similar one with hyperbolic sine and cos. Again, it's not exactly the same. I claim that hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. Kamal is asking which graph is, this is the graph of hyperbolic cosine. We have not graphed hyperbolic sine. I'll let you graph it. Maybe you want to hold off on that because, as some of you may know, graphing is going to be a big part of this course. Right now, we're just investigating properties of the derivative, but very shortly, we're going to apply these properties to the graph. We're going to see how the derivative, or what information the derivative gives us about the graph of the function itself. So we'll get to that later on, and then we can graph these in complete detail if you wish. But for now, you could just plot a few points and see what happens. In fact, what? This is e to the x, this is e to the minus x. So in this part, we're subtracting the two. So it's the difference between the two divided by 2, right? So at 1, at 0, it's 0 because they're equal. And then the difference between the two is getting larger and larger. So you're going to have something like this. And then on the other side, you know that hyperbolic sine is an odd function. So the other side has to be the reflection of the x and then the y. Right, there it is. But again, we'll be able to graph these in a lot more detail later on. Let's prove this identity. Have you proven it already? What is that? Hyperbolic cosine is just e to the x plus e to the minus x over 2. So if we square that and we subtract from that hyperbolic sine, which is e to the x minus e to the minus x over 2, what do we get? So let's expand this. E to the 2x plus this times 2. But e to the x times e to the minus x is This is in real time now. E to the x times e to the minus x. Still nobody? Come on. E to the x times e to the minus x. One, but I mean, there should be no question mark there, right? You add the exponents, you get e to the 0, which is 1, times 2 is 2, plus e to the minus 2x, all over 4. What am I doing? I'm expanding, right? I'm squaring the numerator. So this squared, this times this, the exponents add, right? You know, it's e to the 0. Thank you. Minus, let's do the same thing here. Square this, e to the 2x. This times this, times 2. You tell me. This times 2. Anyone? I see 2 answers. There it is. Jennifer, thank you. Minus 2. Plus this squared. All over 4 again. Where did the 2 come from in the numerator? Come on, you tell me. What am I doing? I'm squaring this, right? So it's this squared, this times 2, plus this squared. Exactly that. Is everybody with us here?
Yeah, and no.
This is a nice final exam question. I mean, very easy. Allison, you're unmuted for some reason. Right, and e to the x, e to the 2x minus e to the 2x. These cancel out nicely. E to the minus 2x, it's over 4, right? E to the minus 2x minus e to the minus 2x. These cancel out nicely. And we're left with 2 plus 2, which is 4 over 4, which is 1. How are we doing? Questions? Right, so hyperbolic cosine squared minus hyperbolic sine squared is equal to 1. Well, let me point out while we're here that if we have this one, we have this identity in the same way that if we have sine squared plus cosine squared equal to 1, we get 2 other trig identities for free by dividing by sine squared or cosine squared. We're going to have the same thing here, right? We absolutely do. If you multiply by 1 over cosine, hyperbolic cosine squared, what do we get? We get 1 minus hyperbolic tangent squared is equal to hyperbolic secant squared. And similarly, if you multiply instead by one over hyperbolic sine squared instead, what do we get? This over hyperbolic sine squared is going to be hyperbolic cotangent squared. Hyperbolic sine squared over hyperbolic sine squared is 1. And hyperbolic cosecant squared. Free indeed. 2 free hyperbolic trig identities. Now, I'm sure you're asking yourself, what about the derivative? Valid question. What is the derivative of hyperbolic sine? Well, hyperbolic sine is just e to the x minus e to the minus x over 2. So differentiate this, which you can do with relative ease, right? The 2 is just a constant, so we'll take that out. Derivative of e to the x is e to the x. Derivative of e to the minus x is e to the minus x times -1. Or 1/2 e to the x plus e to the minus x, which you recognize as hyperbolic cosine. Thank you. The derivative of hyperbolic sine is hyperbolic cosine, very much like the derivative of sine is cos. What about the derivative of hyperbolic cosine? That's the derivative of e to the x plus e to the minus x over 2. Well, who knows? Let's see, perhaps, right? What's the derivative here? Again, the 1/2 is just a constant. We can pull that out. Derivative of e to the x is e to the x. Derivative of e to the minus x is e to the minus x times the derivative of the inside. Chain rule, as always. So we get e to the x minus e to the minus x over 2, which you recognize as hyperbolic sine. So it's a bit different, right? You know the derivative of cos is negative sine, but here the derivative of hyperbolic cos is just hyperbolic sine. And you can work out the 4 remaining hyperbolic trig functions using this. Why don't we discuss the derivative of hyperbolic tangent? Hyperbolic tangent, is it because it's even? Well, cosine was still even, and its derivative was negative sine. So it's just a unique property of the hyperbolic trig functions, right? I mean, they behave similarly. I mean, you have identities which are similar to that of trig functions. They're not always equal, though. They are all even and opposite. I don't know what that means. What does opposite mean? And they're not all even. We saw that hyperbolic sine was actually an odd function. If we work out the derivative of hyperbolic tangent, which is hyperbolic sine over hyperbolic cosine, you know how to differentiate this. Well, cos is not equal to sine, right? You want to be careful there. What does that actually mean? right? Let's work that out. This is a quotient, so quotient rule applies. VU prime, so derivative of, V, the denominator, times the derivative of the numerator. Why don't I write it this way? Just for a first step here, so that everybody's with us. VU prime minus U V prime all over V squared the derivative of hyperbolic sine is hyperbolic cos, and the derivative of hyperbolic cos is hyperbolic sine. Thank you. That's right. So let's use that. Derivative of hyperbolic sine is hyperbolic cos. So we get two of these minus derivative of hyperbolic cos is hyperbolic sine. So we have two of these as well. And wouldn't you know it, we just proved that hyperbolic cosine squared minus hyperbolic sine squared was equal to 1. Thank you. So this is hyperbolic secant squared. The derivative of hyperbolic tangent is hyperbolic secant squared. Very much in the same way that the derivative of tangent is secant squared. Isn't it interesting how these things work out? Let's just look quickly at the derivative of hyperbolic secant. I'll let you do the other two. Hyperbolic secant, which is 1 over hyperbolic cosine, or if you prefer hyperbolic cosine to the -1, the derivative is going to be negative hyperbolic cosine to the -2 times the derivative of the inside, chain rule, right? And the derivative of hyperbolic cos is hyperbolic sine. So this is negative hyperbolic sine over hyperbolic cosine squared, or if you break it up into two pieces, see that it is negative hyperbolic tangent x, hyperbolic secant of x. Similar, but with this negative here. You know the derivative of secant is secant tan. Here you get a negative hyperbolic secant x, hyperbolic tangent x. Shall we take a few examples from the book? You're asked to differentiate. We'll essentially finish around 1 like we usually do. We're not, we'll do a few examples from the book, then we'll discuss inverse hyperbolic trig. Yeah, we'll be finished around 1. A few more minutes. Let's do this derivative quickly. How do we differentiate? Product, right? You recognize this product, so product rule applies. Differentiate the first one, leaving the second one fixed. Plus, leave the first one fixed. Differentiate the second one. We saw the derivative of hyperbolic cos was hyperbolic sine. There it is. What's the derivative? This is something squared. So the derivative is 2 hyperbolic sine of 3x times the derivative of the inside. What's inside? Hyperbolic sine, whose derivative is hyperbolic cosine, times the derivative of the inside. What's inside? 3x, whose derivative is 3. And whoever was asking me, when do you stop? Well, you stop when you have taken the last derivative. You know what the derivative of 3x is. It's 3, that's it. What does hyperbolic even mean? As far as we're concerned, it's just a name for this thing. I mean, it might have a nice connection. But, yeah. One more. Do we want to do one more? How do you go from regular sine to hyperbolic sine? Well, I mean, as far as I'm concerned, first of all, it's only a name, right? So don't let that scare you. You know that it's a combination of exponentials. So if you're comfortable with the functions in terms of exponentials, you can actually work from that. And you're good to go, right? So hyperbolic sine is e to the x minus e to the minus x over 2. Hyperbolic cosine is e to the x plus e to the minus x over 2. Why did they give them those names? Because they have nice properties which are reminiscent of the regular trig functions. They don't all work exactly the same, but they remind you of them. Here, derivative. You've got a ln of something. The derivative is 1 over times the derivative of the inside. Derivative of hyperbolic sine is hyperbolic cosine. So in other words, this is hyperbolic cotangent x. How are we doing? Well, one thing that we don't miss from YouTube is the buffering, right? What about inverse trig, inverse hyperbolic trig functions? Where do we apply this? How do we get 1 over sine? Well, what are we differentiating? What is your function? Your function is ln of something. The derivative of ln is 1 over. Exactly. Where do we apply this? Well, I mean, the obvious Answer is you apply this when the question is asking you for derivatives of hyperbolic trig functions. I suggested that these will appear naturally if you were to run a wire under the weight of gravity. This wire will naturally take on a hyperbolic cosine graph, if you will, or function. And in other words, I mean, how do you see this? Well, you can solve a differential equation, an equation involving derivatives, and the solution is going to be the hyperbolic cosine function. So if you take, after having done calculus, if you take a course in differential equations, if you're in engineering, you're going to have to do 263, a lovely course called ordinary differential equations, and you see all of these things appearing. Well, it's a great course. Differential equations, subject is beautiful. It's a natural progression of calculus. No, it's I don't want to say nice and easy, but what it is. What about inverse hyperbolic trig functions? If y is hyperbolic sine, what is the inverse hyperbolic trig function? Interestingly enough, right, when we were looking at the inverse sine function, we saw that we could not solve, right? If you interchange x and y equals sine x. If you interchange x and y and try to solve, it's not going to happen. However, here, interestingly enough, you actually can solve for the inverse hyperbolic sine function, right? You have y equals e to the x minus e to the minus x over 2. If you interchange x and y and solve for y, it can be done. Let's see how that works. You have this. Let's multiply both sides by e to the minus y. No, e to the y, right? Because e to the minus y is 1 over e to the y. So you have a denominator there. Let's get rid of it by multiplying the whole equation by e to the y. And what do we get here? 2x e to the y is equal to e to the 2y minus 1. Bring this to the other side, and we get e to the 2y minus 2x e to the y minus 1 is equal to 0. Well, what now? Not immediately clear. Does anybody see it? It's a quadratic equation. Quadratic equation in e to the y. If you let u be e to the y, this is u squared minus 2xu minus 1 is equal to 0. Very nice. Very nice. So you can use a quadratic equation. U is negative b plus or minus square root of b squared minus 4ac all over 2a. And if I factor out a 4 from there, 2x plus or minus 2 square root of x squared plus 1 over 2. The 2's cancel out nicely, leaving you with x plus or minus square root of x squared plus 1. But that is your u, which is e to the y. Now you know e to the y is always positive. The exponential is always positive. And this x squared plus 1 is bigger than x squared. Right? Because if you remove that, you get something smaller. And that's just square root of x squared is just going to be x. So what am I saying? If you take the negative, you get x minus something that is bigger than x. So it's going to be negative. So it cannot be the negative square root. So it has to be the positive one. So e to the y has to be x plus square root of x squared plus 1. And finally, take log both sides to see that y is ln of x plus x squared plus 1. In other words, the inverse hyperbolic sine function is this. Something you could not do with a regular sine function, but in this case, you can actually solve for the inverse hyperbolic sine function. So now, if you have that, it's trivial to see that the derivative is just the derivative of this. So derivative of ln is 1 over times the derivative of the inside, 1 plus x over square root of x squared plus 1, which is easily seen to be 1 over square root of x squared plus 1. You know why it comes from the last step, right? I'm just looking at this. So I'm rewriting that right here. The point being that you have to take the positive square root. It has to be the positive. So the derivative of inverse hyperbolic sine, right, is 1 over square root of 1 plus x squared. Very similar to the inverse sine function, right, which had a minus here instead of a plus. It has to be positive because the exponential function is always positive, and this is bigger than x, right? It's bigger than square root of x squared, which is x. So if you had the minus, it would have been x minus something bigger than x, it would have been negative. Yx over, well, you know how to take the derivative of this. Take the derivative of that. It's 1/2 x squared plus 1 to the minus 1/2 times the derivative of the inside times 2x. Question about the derivation? Go ahead. Sean? Well, let me say, we worked out the inverse hyperbolic sine function. You can do the inverse derivation again. you know how to find the inverse, right? You interchange x and y. So you had y equals e to the x minus e to the minus x over 2. Interchange x and y and solve for y. The only trick is for you to observe that you have a quadratic equation in e to the y. That's the only difficult thing. What you mean when you differentiate it? So we're differentiating the ln. Derivative of ln is 1 over. And then you differentiate the inside. Derivative of x is 1. Derivative of this is that. That's all. Then put everything over common denominator, which is going to be this. And you get square root plus x, which is going to cancel with the square root plus x. Leaving you with that. Why did I flip the x squared into 1? Only to illustrate. You know the derivative of inverse hyperbolic, inverse sine function is 1 over square root of 1 minus x squared. So it's almost the same thing again. Questions? Think about this. And here's what I would like you to do. We did not work out the derivatives of hyperbolic cotangent nor hyperbolic cosecant. You can work those out. And you can find the remaining 5 inverse hyperbolic trig functions as well. And you can differentiate them and see what those give you. These are nice exercises. You can do that once you've finished with the midterm. Top left line to the second line. So this to there. Common denominator for the stuff in the brackets. And then it's going to cancel with this denominator. The numerator here will be the same as the denominator here. They just cancel. Common denominator is the quick answer. All right, we're already 11 minutes past our time, which was already 15 minutes past the real time anyways. We've done more than enough. Thank you all for coming. And sorry about this YouTube versus Zoom mess. Hope everything will be good to go next week. You guys have a good weekend. Good luck on the exam. And I will see you on Monday. You guys have a good one.